Good afternoon, everybody, and welcome to quite a cool webinar I've been looking forward to for quite some time. And it's going to be integrating stiffness analyses into global models. My name is Jacobus Oberholster. I'll be facilitating this webinar. And you can also see my email address in the bottom left there. So you're welcome to contact me if you want any additional information, if you're looking to chat a bit more about the topic, or actually just any topic related to IDEA StatiCa or Prokon, whatever it might be. It'd be lovely to hear from you. We also do have a live chat as we speak, so you can actually post some stuff in the chat if you have any questions. I would really encourage you to do that. If you do have a question versus waiting until the end, I've decided just to actually leave a formal Q&A time, just because of the latency we can have between when you post the question and when I actually answer the question. All right, so feel free to post something in the chat if you have a question. Otherwise, you're welcome to get hold of me after the webinar. So, all right, without further ado, let's jump into our agenda. And we've just had our nice little introduction. We're going to look at understanding connection stiffness a bit. Then we're going to look at calculating connection stiffness using IDEA StatiCa. And then we're going to look at incorporating connection stiffness into Prokon Frame. So that's Prokon's frame module. Then we're going to run an analysis and interpret the results. We're going to chat a little bit about the relevance of stiffness analyses, and then we'll of course have a normal conclusion. So right, let's jump into IDEA StatiCa. We will just look a bit at stiffness analyses. All right, so we've got 4 connections modeled here, and any connection has an actual, so a real life stiffness, right? So if you think of shear plates, fin plates, end plates, we tend to see them as pinned. So what we assume with something being pinned, of course, is that it doesn't translate any rotational forces, which means the actual beam has to absorb all of those moment forces, which results, of course, in a larger beam. Then we go to the opposite side of things, which is a fixed connection. So if we go here to C4, that should be a bigger connection actually. So yeah, if we look at this, we would probably assume out of the gates that this should be a fixed connection, right? So we assume that a connection like this can transfer moment forces. All right, so in that case, the beam itself will be a little bit smaller, and we'd of course expect a certain effect from the change between pinned and fixed. Okay, but in reality, you know that even a shear plate, so even if I go to C1, which for all intents and purposes I would take as a pinned connection, you know that in reality, if there was to be an imposed load here and this beam would bend, that these bolts and this weld can actually transfer some of the moment some of the moment forces. So in actual fact, no connection is purely fixed or purely pinned. They're actually somewhere in the middle, and they tend to either go towards pinned or they tend towards fixed. Okay, now just looking back at the agenda, we might jump in between some of those points as we just go through our discussion. But this is in general is a topic that isn't explored a lot because of how complicated it can get once we get to 3D models. So if we look at a three-dimensional model in frame and so forth, because it becomes really tricky to actually continuously update rotational stiffness values and so forth as we model. But we'll chat a bit more about that when we get to frame. But where this is actually quite cool is where we move, or where we especially move outside of the normal scope of connections that we're used to. All right. So for whatever reason, you're not necessarily going to look at a standard haunch or apex or whatever it might be. You're investigating a new type of connection that's in a sense been forced onto you due to geometric constraints or whatever it might be, and you assume that it's fixed, right? So when you get to your global model, you're going to assume fixed, but in actual fact, do you know? Are you sure that the specific connection type is actually rigid enough to be considered fixed, and then vice versa? All right, if you consider a connection pin, but it's actually rigid enough that we won't classify it as pinned, then you might oversize your member, so your beam, or it might be that you're going to pull quite a significant amount of moment into your connection, and you can actually have some failures in this location here. Okay, so we'll see more of this in action as we progress through our workflow, looking at especially incorporating these stiffness values into frame. That's going to be really helpful to really understand what we're working with here and why it is important to consider. So right, within IDEA StatiCa, you can just model any connection as per normal. If you go to the project space, you can see you can have your different analysis types there, and I set all of them to ST, which is the stiffness analysis type. From here, if I go to the design tab, we have to set an analyzed member, in this case, which will be the beam, and we have a few other things we can set up. So you can see the beam is the analyzed member. If I click on the column, you can see I can set that as the analyzed member as well. Here at the bottom, we have the theoretical length for MY and MZ, and that is basically just your effective lengths in the about the strong axis and effective lengths about the weak axis. So MZ is the weak axis and MY is the strong axis in the case of IDEA StatiCa. This will have no effect on the actual rotational stiffness of your connection. However, it will affect the classification of your connection. So whether it's considered a pinned or rigid connection. Then also, you don't want any eccentricities in your model in terms of these position parameters. Okay. Then when we get to our load effects, the specific load effect we incorporate determines the stiffness that will be calculated for us. Okay, so if we want translational, if we want to calculate translational stiffness, we put in an axial value. In this case, we want the strong axis stiffness or rotational stiffness, and therefore we have an MY value. In the event where your connection is not symmetrical, you would want to test this both in the negative and the positive direction, because you'll get two different rotational stiffness values. Okay, so that is important. And in general, you would want to create a separate load effect for each direction under consideration. All right, so that's the basics. You can also set whether or not the system is braced. So if you look at project settings, we should have somewhere in all these settings, we should have the option to set whether or not our system is braced. You can see that under calculation and checks, we can tick whether or not this is a brace system. So brace system would be global. Okay. Now again, that won't affect the actual rotational stiffness value, but what it will affect is the classification of the connection itself. So, all right, let's get into calculating. So we're now going to calculate the rotational stiffness for the specific connection in the specific direction. Okay, so we're waiting for that calculation to run, and then we'll just look at the outputs. We'll do that for each of the 4 connections, and then we'll go to frame and have a look at stuff over there. Okay, so we're not so much worried about the stress strain outputs. Okay, we're not too worried about that. So we're going to go to check, and we're going to look at the rotational stiffness value there. So that minus 50 is just a random number. Okay, and I'll explain why we use a random number shortly. But okay, we've done our analysis, we're in check, we go to rotational stiffness, and there's quite a lot going on here. So I'm going to see if I can increase the size of this graph a little bit. There's a lot to understand here, but basically, I hope that you can see there's a little orange line there, and then there is a blue line over there. Now, if you, it's not as easy to see here, but you can actually see there's a green curve, and that basically is the stiffness curve of your connection. If that curve is on the left-hand side of that orange line over there, the connection will be considered as rigid. If it's below this blue line, it will be considered as pinned, or in this case, simple. So they've actually changed the class naming for your pinned to rigid connections. And if it's in between these two, it will be semi-rigid, basically. Okay. So what we're interested in is this SJ ini. So that's the initial rotational stiffness. You can see there. And then there's also the secant rotational stiffness. Now, there's quite a bit to understand here in terms of if you really want to get down to the nitty-gritty of the stiffness analyses. I really recommend looking at some of IDEA StatiCa's training that's freely available. In the advanced training, they actually cover, there's a whole section on stiffness analysis. All right. Here, if you look at the SJR, that's the limit value for a fully restrained joint, which in this case would be a fixed joint. And there's the limit value for a simple joint. Okay, so P for pinned and R for restrained. Okay, so because of that minus 50, that's sort of a thumbsuck value, we are going to look at the SJ initial value for now. And we can see that's meganewton meters per radian. And so we'll keep that in mind. So what I'll do is for C1, I'll write that value down, which is 1,9 meganewton meter per radian. Okay, cool. Now what we're going to do is we're going to move on to C2. Oh yeah, also that connection was classed as simple, so it is a pinned connection technically. Okay. Here, luckily, it kept this analysis for us for C2. You can see there's the orange line. So there's that orange line just sticking its head out over there, and there's the blue line. And you can see that this intersection point over here falls in between those two lines, and therefore it's a partially restrained connection or semi-rigid or semi-fixed or whatever you want to call it. Okay. We can see that the SJ initial value or the initial stiffness value is significantly larger than it is for the previous connection. So I'm going to write that down, 58,7, and we are going to proceed onwards with the next connection. So, oops, not C4, but rather C3. But okay, C4 is going to load anyway, so that is fine. Okay, so let's have a quick look at C4. So you can see here, it's just, you can actually not see that orange line over there. I'm just going to zoom in some more until you can see the orange line. Okay, there's the orange line. All right. And so you can see that this connection is now classed as fully restrained or fixed. And its initial rotational stiffness is 126.3. So also very large, or much larger than the previous connections. So lastly, let's look at C3. Accidentally skipped that one. And this one is considered partially restrained, and its initial stiffness is 22,2. Okay, now just something interesting. If you look at this connection, you see those little plates there and everything. I would consider this to be fixed. But then C2 is actually stiffer than C3. Although I wouldn't necessarily have thought that just looking at the two connections. Okay, so oftentimes we might not necessarily make the correct assumption if we just look at the connection. Okay, so we've got those values written down, or at least I've got them written down. So I'm now going to go to frame. I've set up a model here, so I'm just going to explain a bit about the model. So what this model is it's a 2D frame, all right? So to doing it in 2D just makes it a lot more simpler to show exactly what's happening. So that's why I've gone with a two-dimensional frame. All right, so we've got our columns here, and we've got our beams running across. Our supports are fully fixed, and then those little blue dots indicate that there are springs here. So that spring is in this location over here, over here, over here, and over here. All right. So then when we go to spring elements, or rather before then, I just want to show with beam loads as well. I've ignored self-weight, but it's a minus 10 kilonewton per meter UDL on each one of those beams. Okay, cool. So we go to springs. We've set up our springs and we've set their orientation as well. Luckily, the orientation of the spring is not so important for a 2D frame. In the event that you are working in a three-dimensional frame, the orientation node would actually be quite important. So the orientation node determines the x-axis of the spring itself. Okay, so I've created the 4 springs on the right-hand side. As you can see, the spring type and name. There's C1, C2, C3, and C4. Kx and Ky are translational stiffness values, which I've made 1,000,000. Just because I don't want translation. I don't want to. I assume that the translation is infinitely stiff, all right? Which in itself it isn't, but we're not thinking about that. We're thinking of the rotational stiffness, which is something that a connection is much more susceptible to, and what in itself has it got a lot. It's got a much bigger effect. Okay, so C1. You can see here that RZ, so that is the rotational stiffness about the Z axis, and Z is down there, is 1,900 kilonewton meters per radian. So of course 1.9 meganewton meters goes into, so it times it by 1,000 to get kilonewton meters per radian. Okay, and I've got those 4 values in here. So I've got the 4 connections simulated with their rotational stiffness. And then if I can now assign a spring type. Okay, so I'm going to assign the same spring type to each location. So I'm going to go, these guys are C1, which was classified as a pinned connection or a simple connection. And I think that's maybe why they've changed the terminology, because pinned could be misleading. So if it is truly pinned, we should see 0 moments at these locations. Okay, so I'm going to run the analysis. I'm going to take note of the maximum deflection. Okay, so max deflection for C1 is 41,8. And then we're going to look at the moments. So view output, beams and forces, and then I'm going to set this to X moments. And you can see that the bending moment or bending moments aren't completely 0. You can see there's actually a little bit of a hog right there. Okay, even though the connection was classified as pinned. Okay, let's also take note of the maximum bending moment, and in this case it's 102.37. Of course, the stiffer the connection is, the smaller that amount should, or that amount should decrease. Okay, so let's go back to our input. We're going to change it to C2 now, which is considerably stiffer than C1. We'll go to analysis and we'll rerun the analysis. Okay, so we should see a change in deflection and in the bending moment. Right, so it's previously our deflection was 41.8. For C2, it's now 20,38. All right, but just changing the rotational stiffness value. I'm going to go to view output, look at beam forces and X moments, and we see a reduction there, a considerable reduction from 102.37 to 60.61. 1. Okay, now remember that initial minus 50? Well, that was a thumbs up value, and now we have an actual value that we can read off, which is 64.39. All right, so for C2, 64.39. So we're going to go back. We're going to enter that value for C2 for the bending moment, and we're going to run our analysis again and see if there's been any change in the stiffness. Okay, let's go and change again. So spring elements, I'm going to go for C3, which is not as stiff as C2. So we should see a increase in deflection and bending moment in the middle of the beam. So reset. Going to start it all off, and we see there from 20.38 to 23.43. So 23.43, and then we want to check the moment as well. And there, instead of 60.61, the bending in the middle of the beam has now increased to 66.57, which is what we expect. And then we take note of the moment here on the edge, 58.43. And then lastly, we need to look at C4, which should have the largest moment here and the smallest moment here in the middle. Okay, so we go for C4, that is considerably stiffer than the rest of the connections. Go to analysis, reset, and start. All right, so the smallest deflection yet, 19.25. And then we take note of the bending moment, which in the middle of the beam is 58.4. And then on the edge is 66.6. All right, so this was in working with the initial stiffness values, but now that we have an actual value for the bending moment at that connection, we can now plug that in, and then we can read off the secant stiffness. Okay, so I'm just going to set everything up here again, that we have our spring elements. I'm going to go back to IDEA StatiCa, and I'm going to ignore C1 just because I couldn't take a good read of the value there, but I'm going to change the bending values for C2. And what we're hoping to get is actually that that these two values are as close as possible. In this case, they are identical, so which is a really good sign. What we then want to do is change that bending moment and see if there's any significant changes in the rotational stiffness. All right, so I'm going to go to design. It shouldn't be too big. I can't expect a massive difference, but it means that we're just getting closer and closer to what we would expect in reality. So I'm going to go load effects, and MY I'm going to make for C2, I'm going to make minus 64.39. And then I'm going to rerun the analysis. Okay, just waiting for that to be picked up, and then I can run the analysis again. All right, so I'm going to click calculate. Because remember, as it calculates that every time the stiffness value changes, your bending moments and deflection are going to change as well. So you can see already, well, okay, maybe not yet. Let's just look at what our outputs are going to be. Let's go to, okay, it's just loading quickly. Remember for C2, it was 58.7 meganewton meters per radian. Let's look at it now, if there's been any significant change. And it's 58.7, which is great. Okay, so that's awesome, which means we can pretty much go C2 is sharp. Okay, so C2 is sharp. and we see that it's partially restrained, so that's fantastic. All right, let's go on to C3 and take a note. You can see here that there's actually a difference between the initial and secant rotational values, and that comes down. You can see that for C2 it was identical. Here they're not identical. So I'm going to go to design and I'm going to change that bending moment value. So luckily in this case it's going from 50 to 58.43. So I'm not expecting a big difference. So we make it 58.43. And just waiting for it to load, and then we're going to run the calculation again. So cool. When there's a change, now with these new values, we instead of reading off the initial stiffness values, we read off the secant values, and then we start this whole process from scratch again. All right, so you can see now, as we work through this, there's a good reason why this isn't necessarily incorporated holistically in our design workflows. And that is because it becomes an incredibly complicated and iterative process. All right, so you see that you have to actually go back and forth, so multiple iterations to actually get all the values to remain constant, and then and only then can you sort of go, okay, well, no, not then and only then. That's a bit extreme, but you need to run through a few iterations to check that all of those values get as close as possible to each other and that they don't change. Then you know, okay, cool. I have a successful stiffness analysis and I've successfully incorporated that into my global model. I'm going to go back to check now, and let's just see, is there any change in the rotational values? And then I might just update the rotational stiffness. Okay, and here there's actually, I don't think there was a change in the initial. I think that remains constant, but there's a slight change. I think it was 25, it's now 24.8. So I'm going to note a secant rotational stiffness of 24.8 mega Newton meter per radian. And then lastly, we're going to do it for C4 as well. And then those are the values we're then going to assign to the springs. And again, here, those values, there's a minor difference between the two. So 127.7, I'm going to go back to design and change my load effects. So change it now to 66.6. And then run the analysis again. So minus 66.6. And this connection isn't symmetrical because there's nothing at the top, so we would technically have to run it in both directions as well. So let's just give it a second to think. We run the calculation again, and what we're interested in now is not the initial stiffness, but the secant stiffness. And we're going to go back, make the updates in frame, and then check. We're not going to do this a second time around. We're just doing that once off, just so that you are aware of the workflow. Okay, so we should be almost done, and then we can have a nice look and see what's happening. Also, I've developed or I've written quite a few articles or blogs, and then I have some vlogs as well on stiffness analyses and how to go about it. I think it's something I would want to do, even as I design. That I'd want to check how my connection gets classified through a stiffness analysis. What we'll look at the end is going to be quite nice as well, where we look at setting a connection as fixed and then checking what is the output and at what rotational stiffness value do we actually get an equivalent output. Okay, so we can see here 127.7 for the secant, so that's great. So I'm going to record that 127.7. We're going to go back to frame and just update those values. Okay, so C2 remained constant, which is great. C3 is the only one that's had quite a substantial change. And then we're going to do the same for C4, which is going to be 127,700. We can then run through the analyses again and check. So let's run them again. We're interested in this top beam for now. We're just going to see, is there a significant change in output? So our deflection hasn't changed. It's decreased by 0.01 millimeters. And then our beam forces, let's see, our maximum bending moment was 58.4 last time. It's now 58.38, and it's changed from 66.6 to 66.62, which means that we're very well in the ballpark for this connection and its stiffness values. So we're happy. We know that what we've simulated here has converged in a sense, and we can use that stiffness value then as we proceed through the rest of our design. Okay, let's do one more change where we set it all to C3. And let's have a quick look at the change there. Interested in deflection and bending moment. Okay, so deflection has changed from 23.43 to 22.96. And then we look at our output, look at beam forces, and it's changed from 66.57 to 65.64. And that moment has changed from 58.43 to 59.36. So maybe you go, okay, cool. This is within an acceptable range. I'm not going to run through the iterations again. I'm happy with this as is. Or you actually work through this process again for C3. Okay, so you can have a frame template where you have all of your connections modeled in IDEA StatiCa. You can determine their rotational stiffnesses and you can incorporate those into your global design to have an accurate reflection of where your moments are going to and so forth, and then to design accordingly. The cool thing is that unfortunately, Frame doesn't link with IDEA StatiCa. But in the event where you have a program where you can set up these rotational stiffness values, you can get load effects, you can then export it to IDEA StatiCa and actually design the connection with the actual bending moments. Even though you consider this as pinned, it might have a bending moment that you need to incorporate. Okay, so that's interesting. I think I quite like the idea. I know that it adds an element of complexity, but it is one of the design approaches that you can actually follow. I think it is called the flexibility method, where we actually take into consideration the real rotational stiffness of a connection and incorporate that into our model. Okay, so what we're going to look at now is I'm going to save this. I'm going to open up another model. So unfortunately, I have to close this, but I open up another model and we are going to look at the stiffness model comparison. So we're going to do two comparisons. So this model doesn't have springs. So we're going to look at the output when we set the beam connection to the column as pinned, look at the deflection and bending moment, and we can do the same then for fixed as well. So we're going to look at those values. Then we're going to go back into our model with the springs, and we're going to see how do we simulate pinned and fixed, and what is the actual rotational stiffness value for that. Okay, so you can see here for this model, it's exactly the same. However, we don't have spring elements. So these are spring types, but we don't have spring nodes. I could even, yeah, so there aren't any springs. Those little dots you're seeing there are showing that these beams, these elements are pinned where they connect with the column. Okay, exactly the same beam load, so minus 10 kilonewton meter running across the beam. We'll go to analysis and we'll start and we'll take note deflection and bending moment. Okay, so maximum deflection for pinned is 53.4 which is already more than C1. Okay, so C1, the deflection was 41.8. Okay, here the deflection is 53.4. And then we want to look at our maximum moment. We know on the edges it'll be 0, but in the middle we'll have quite a large moment of 125 kilonewton meter. 125 kilonewton meter, whereas the moment for C1 was 102.37. Okay, maximum bending moment in the middle of the beam. All right, so that's for pinned. We're going to go back and we're going to change these to fixed now. So where there's a P, I'm going to put in an F for fixed and do that for all of them. And we're going to run our analysis again. All right. In this case, the maximum deflection is 18.19. And that actually is very close to our connection C4, which was 19.25. So I'm going to say fixed is 18.19. And then let's look at the maximum bending moment. It is 56.35 in the middle. And then it's 68.65 on the edge. Okay, for our C4, it was a maximum bending moment of 58.4 in the middle, and the bending moments on the edges was 66.60. So you can see that connection C4 really is tending towards being a fully fixed connection. Okay, so we've got those values. We're going to go back to our previous model, and we're going to look at creating new springs, and we're going to see what must their rotational stiffness values be in order for them to be to actually have the same values that we just calculated now. Okay, so we're just waiting for a frame to open up, and then we are going to run through that. Also, just a quick one, if you want my model, if you want these models, if you have access to Frame and you want them, you're welcome to get hold of me after training. So you can just send me an email and you can ask that I send these models through to you so you can have a look and maybe even just play around with them a little bit. Okay, so remember this one where we got our springs again. So spring elements, I'm then going to create a new spring type. So I'm going to say this is P for pinned. Again, translational stiffness is going to be very stiff because I don't want, I want it to be, translationally stiff completely. And now it's RZ. Okay, so what should RZ value be in order for us to replicate those values from before? So for pinned, it actually needs to be 0. Okay, so I'm going to assign pinned springs on the edges, and we're going to compare the results. Okay, so rotational stiffness is 0. All right, so we're expecting the same deflection and bending moment. Right, and there you go. 53.4 deflection, which is spot on. And what we're expecting in terms of the bending moment is 125. Let's have a look. And there's 125. So you can see that no real connection will be perfectly pinned, as in having a rotational stiffness of 0. But that is what we assume when we use the pinned settings. Okay, let's have a look at fixed. So I'm going to say F here for fixed. Again, translational values are going to be big. C4 was 127, so I'm going to make C4 200,000. And then I'm going to change the spring type to F. Go for the analysis again. and we're expecting about 18.19 in deflection. So there's 18.87. So you can see, even at a value of 200,000, we're still not quite at fixed. Okay, so I'm going to go back. I'm now going to make this guy 10E6, or wait, let's make it half a mil rather. Let's look. 80.47, so still not there. Okay, let's make it 10E6 as with the translational stiffness. Let's see. And still not. So 18.21 instead of 18.19. Look, that's incredibly close. So we're going to look at the beam output quickly, look at beam forces. We're expecting 56.35 in the middle. So we've got 56.38 and 68.65 on the edges. We've got 68.62. Okay, so that's incredibly close. But you can see that assuming something is fixed is really taking it incredibly far in terms of what it would actually be. Okay. There are cases where a connection will be seen as infinitely stiff, to which I go, yeah, cool, that is fixed. All right. It is infinitely stiff in a specific direction, though. But then we go, okay, cool, that connection is fixed. But I hope that what you've seen through here is that it's not as simple necessarily as saying a connection is pinned or fixed, because it's not really either. It's somewhere in the middle, and it tends more towards pinned, or it tends more towards fixed. But it's not perfectly either of them. It will never be. So let's look again at why, or just chat about why, or what is the relevance then of doing a stiffness analysis. Um, Well, you've seen the relevance now. You've seen that the rotational stiffness can have a significant effect on the maximum bending moment and the deflection and hogging moments as well. You've also seen that setting something just as purely pinned or purely fixed is not really accurate to what it actually can be. And in the event that you classify a connection, you can much more accurately simulate what would really happen in the global model. However, once we start doing this in 3 dimensions and you've got maybe 4 members coming in at one point, it can get incredibly complicated. Even if we just had to add an additional, so create a copy of this frame here and connect it in the Z direction, we already are entering into a space where it can become incredibly complicated and time consuming to actually calculate, to go to IDEA StatiCa, calculate all of those rotational stiffness values, come back, incorporate them, and assign them correctly. It really can become incredibly cumbersome. And the reality is that working with purely fixed and purely pinned has worked. We don't have buildings collapsing on us. It works. There's a reason why it works, and that is something to take into consideration as well, as there's a reason it's worked. I would say again that in the event that you have a connection that doesn't fall within the normal spectrum, again due to geometric constraints or just due to structure geometry, I would really recommend that you actually do run a stiffness analysis and check that is your design of the connection, or just the look of the connection, is it actually tying in with what you've set up in your global model, right? So where we could make a real mistake is modeling something as fixed, but when we do the stiffness analysis on the connection itself, it actually turns out to be pinned or semi-rigid and very close to pinned, to which end we have a problem, right? The way that the structure will behave will be very different if we actually incorporate the rotational stiffness of that connection. All right, so that is our webinar done and dusted. If you have questions, you're welcome to ask. Otherwise, what you can do is you can always get hold of me via email. Send me a mail. If you want the model, send it to me. I'll send it through. Even if you just want to see how you model stiffness within frame, or how do you model springs. In this case, we've actually had a real life application where they had like a type of rubberized connection, like an elastomeric connection, and they needed to simulate the that stiffness in their global model. So we've actually had something like this happen before, where it was necessary to simulate the model just like this and actually check what is the effect on the bending moments and deflection in the model. We might have software packages that incorporate these rotational stiffness curves and actually allow you to simulate a much more accurate, or to simulate your deflections and bending moments much more accurately. And that's something, once it's available, we'll chat about that. But other than that, that's it from me. Thank you so much for tuning in. I really hope that you've enjoyed this. This is a bit more of a niche topic. So, yeah, I don't expect necessarily too much to come from this, but maybe it's just been some really good food for thought and it's just tickled you a little bit. Um, so, yeah, hope that you've enjoyed it. Otherwise, hope that you have an epic afternoon further. And then I'll hopefully see you in future webinars. So we'll be looking at the design of castellated beams in next month's webinar. Um, and yeah, looking forward to that one as well. I'll still hang out for another minute or so if there are questions. Otherwise, yeah, enjoy your afternoon further.